Hello and welcome to this Studying Ancient Materials video, where today we're going to be talking about rocks and minerals. First off, we should really cover some definitions. Now, a mineral is a crystalline solid that has a recognisable chemical formula, such as this quartz here, which is basically silica, that is silicon and oxygen in a crystalline structure, whereas rocks are a collection of different mineral types. So here we have a sandstone, for example, which consists of some quartz, some iron oxides, and possibly some clay minerals. So it's a combination and a agglomeration of different mineral types. Now, the reason we care about minerals and rocks as archaeologists and anthropologists is because they are a fundamental aspect of human material culture. We use them to build buildings, to make roads, to construct tools. There are many functions of rocks and minerals, and understanding their production, their use and procurement can give a tremendous insight to human society, both in the present day and in the past. Rocks and minerals have been a fundamental aspect of the human material world since our earliest human ancestors. Rocks such as flint and obsidian were used to fashion tools such as arrowheads and hand axes, whereas larger stones were used to construct monuments to identity like Stonehenge. More recently, rocks and minerals have been used to construct houses, buildings, bridges, aqueducts, roads, statues. Indeed, rocks and minerals are all around us. Understanding them is fundamental to understanding human culture. Therefore, it's important to have a vocabulary and a language for understanding and investigating rocks and minerals. There are some key descriptive terms that are incredibly useful. Crystal form, for example, can tell you how the crystals are structured. Cubic or trigonal, for example, or even not visible. Fracture, how the mineral breaks. Does it fracture in a crystalline way? Is it irregular? Is it conchoidal, as flint and glass would be? Hardness is another key descriptive term. Is it, for example, harder than your fingernail? There is a hardness scale you can use, but in the field you can basically give it a little scratch and see how soft or hard it is. Another really useful descriptive term is streak. That is, when you scrape a mineral along a white tile, what colour line does it leave behind? It can be a really characteristic way of understanding differentiating between different minerals. At this point, it's worth having a look at some examples so we can see what these terms mean with a sample in front of us. This is an example of flint, which is a very fine-grained quartz. It's basically a silica mineral which has a cryptocrystalline structure, so when it fractures, it's conchoidal. Now, there are lots of different varieties of silica mineral which are quite similar to this. Flint is one, obsidian is another. Silica deposits such as flint and chert originate from radiolarian skeletons. So that is basically fossil radiolarians that have been found to date to the Precambrian time, some 3.96 billion to 540 million years ago. In Dorset, flint can be found in primary deposits within the chalk and limestone beds, and in secondary deposits within sands and gravels. This is another example of a silica-based mineral. This one's quartz. We saw a sample earlier. It's one of the many varieties that primarily consist of silica or silicon dioxide. Quartz, it's the second most abundant mineral in the Earth's crust after feldspar, and it occurs in nearly all acid igneous, metamorphic and sedimentary rocks. It's highly resistant to weathering and tends to concentrate in sandstones and other detrital rocks. Sedimentary quartz serves as a cement in sedimentary rocks of this kind. This example is a perfectly formed crystal quartz. You can see the really well-formed crystal structure there, which is characteristic of this type of mineral. This next one's a mineral that should be familiar to you if you watched my metals video. It's called Hematite, which is an iron oxide mineral with the formula Fe2O3, and it's widespread in rocks and soils. It's got a very common trigonal crystalline structure to it, which makes it highly recognizable. It's Its fracture is uneven to subconchoidal. It's quite a hard mineral, a hardness on the Mohs scale of around 6.5, and it's used as an ore mineral but also as a pigment in the manufacture of reds and blacks and ochres, etc. This next lovely sample is a specimen of slate, which is a fine-grained clay metamorphic rock that cleaves or splits readily into thin slabs, having a great tensile strength and durability. There are some outcrops of slate in Cornwall, but the main supplies in the British Isles at least are in North Wales and the north of England, and it's a rock that's used extensively for roofing in the building industry. Its characteristic cleavage really lends itself to these platy functions. This example is a specimen of Purbeck Limestone, part of the Purbeck group in the Upper Jurassic to Lower Cretaceous lithostratigraphic group. That's a sequence of rock strata in southern England. The name is derived from the district known as the Isle of Purbeck in Dorset, where the strata are exposed in the cliffs west of Swanage. The Purbeck group is famous for its fossils of reptiles and early mammals. Indeed, it's part of the Jurassic coast. Some of the rock beds are locally called Purbeck marble, and this derives from the sedimentary rock's ability to take a polish once cut, but it's not to be confused with a metamorphic marble. They are quite different in form and structure. This one's a sample of a rock core taken from an igneous porphyry rock off the west coast of Scotland. Porphyry rocks are made up of larger phenocrysts set in a background of smaller uniform crystals. Igneous rocks are typically more dense in mass and more difficult to work given their highly crystalline texture and relatively poor cleavage structure. The reason it's important for archaeologists and anthropologists to understand rocks and minerals rather than just the artifacts made for them is because it allows us to ask bigger questions about the material world. A good example is the Langdale Axe industry. Now, Langdale axes are a type of Neolithic polished stone axe. Now, through studying them petrographically, that is, studying their mineralogy, it was possible to identify the specific quarry they came from. And that quarry was located in the Lake District, yet there are distributions of Langdale axes across Britain and Ireland, so we know they were moving considerable distances, and we can start to think about trade, exchange, mobility and identity. And in fact, there's a particularly large cluster of them in East Anglia, and it's possible that this area had a particular affinity with this type of material culture and this type of hand axe. So being able to piece together the mineral composition, its understanding, its type, allowed archaeologists to disentangle an industry that covered the whole of the British Isles. Now, another word you'll often hear when it comes to rocks and minerals is lithic. Now, quite simply, that comes from the Greek lithikos. It means stone. But in an archaeological context, it tends to be associated with those things made. So Stonehenge may be described as a megalith, whereas a small flint blade could be a microlith. So lithic tends to be associated with the production of things from stone, i.e. tools and monuments. Now, it's also one of the most studied areas in terms of rocks and minerals in archaeology. Now, that's down to the many millennia of human use of lithic tools as their main type of material culture that we can see in the archaeological record. Of course, organic materials were probably being used alongside lithics, but we do see an awful lot of lithics preserved. So understanding their production, their use, their function and their consumption is a fundamental part of understanding many millennia of human tool use. So I thought, rather than show you a few flint artifacts, I will show you a couple of examples. Why don't we try and knap some flint so you can see the process in action. Now, knapping is the term used for the process of reducing a flint nodule into a finished artifact. And the first part of the process really is hitting the flint nodule with a hammerstone, as you can see here, to remove large flakes that can then be either worked down into smaller artifacts or to break it into smaller pieces that can be worked. And you can see here the reductive process with this larger nodule, the continued percussion and hitting, impacting, it removes flakes, and it's slowly reducing this flint nodule into a usable core. Now this process could be repeated and repeated and repeated, and the nodule itself becomes worked into an object. As I say, the flakes that are hammered off can also be used as tools, as artifacts, and worked into smaller things, as you can see here. So this is a smaller fragment. After this initial percussive phase, the flakes and core can be subsequently worked down into finer artifacts using pressure flaking, which is when you push against the flake itself to force tiny fragments off. And you can see here some of the key characteristics of flint. You can see bulbs of percussion, you can see percussion lines, and you can see that type of conchoidal fracture that's characteristic of this mineral group. And here's one we made earlier, an arrowhead made from flint, and you can see some of the key characteristic marks on here. You can see the remnants of pressure flaking on the edge where the edge has been refined. You can see the conchoidal shape of some of those fractures, and you can see just how fine that edge is. And indeed the edge thickness of flint and obsidian is one of its key material benefits. And right up until relatively recently, obsidian tools, obsidian bladed knives, were still used in eye surgery. So before laser eye surgery, the thinness of the edge on lithic tools were still used in modern medical practice. And this last artifact is a hammerstone. You saw me using one earlier. This is an archaeological example, and you can see on here some of the key characteristics you would find on a hammerstone. They tend to be fairly smooth, made from quite a hard igneous rock typically. Beach cobbles make great hammerstones, but you can also see the fractures on the working face where it's been used and reused and used again to routinely hammer on flint to remove those large flakes. Now that's just about it for this rocks and minerals hands-on practical session. I hope you've all enjoyed it and I hope you've got something out of it, and I'll leave you with one more rock.